Reuleaux, yeah, it's good.
From Kent University, Programming Languages and System Group. I'm presenting talk on programming and refactoring different types. Yes?
Yes.
And just usual notice, if there is emergencies, the exit is there.
Okay, yes. Thanks very much for inviting me. It's an honor for me to be here tonight. The idea is to talk 2/3 of my time about programming with dependent types in general. I will have a few examples with Idris, from Idris, and roughly talk 1/3 of the time about what I am doing. I'm using a slightly smaller language, Py4all. I come to Py4all later. I mean, the thing is, I figured if you're not familiar with dependent types, I'd like to get across some ideas. I'd be happy if I can whet your appetite if you, at the end of this talk, maybe want to try out a little Idris and some examples. And any research efforts are very special and may not be. I will not. I doubt you will want to download my code. I'd be happy if you do so, but I'd be happy if I get someone creators. If I can whet your appetite and you want to download it, and this clock will keep you on track. So, what are dependent types? This is a very simple definition. Dependent types are types that may depend on values. And in order to illustrate what I mean, this is a very simple example. Vectors are like the very basic types one comes across in any tutorial on any dependently typed language. There's more examples. We'll get to other examples, even simpler examples. Yeah, these are like the standard examples. So you may be familiar with a list. I will assume that you're interested in programming language, and some of you have an interest in functional languages. Yes, I assume that you have not a lot of experience with dependent types. Is this right? Yes.
Functional languages, you say?
Pardon me, functional languages. Yeah. These very first lines are something that may be familiar to you. This is just a list of 4 elements, yeah, and you write them down in these brackets. This may be what you know from ML or Haskell or whatever functional language. And this is just some simple interaction with the system. Well, I asked what is it? I just type in this list and the system answers, well, it's a list of integers. It's nothing very surprising. I have to do a little more. I have to say, well, I want these 4 numbers in brackets to be understood as a list, because for vectors there's the same notation. Yeah, so it's just to disambiguate lists from vectors. And if I want these same 4 numbers to be understood as a vector, which this the function does for me, well, I get the answer from the system. This is a vector of length 4. So you agree with me that this information is richer than just saying it's a list. It has the notion of a length built in. Yeah?
It's automatically derived.
Pardon me?
It's automatically derived.
Well, in this case, it's automatically inferred. Yeah, the system is clever enough. I could have. I mean, these underscores are saying, I don't know more precisely what kind. Please tell me, system. Yeah, and the answer of the system, this 4, replaces this underscore. So So the size of the vector is known as 4, and the type of this vector is an integer. And well, this is the type, yeah? A vector of a certain size of some type. In this case, a list of 4 integers. Here is a very similar other example, a list of 2 strings. Yeah?
Well, if you say list with 2 underscores, it will answer list 4 integer, right?
If I say list with 2 underscores,
yes,
this will not be correct. Because if I, how should I say, the list has only one variable. It can be a list of string, a list of integer, a list of whatever you may be interested in, whatever type you may be interested in, but it does not have the notion of a length.
okay.
Yeah? So the list, we'll come to the definition of lists in a couple of slides. Maybe I should skip forward, I don't know. The list would be written list of A. Just forget about this. Yeah? So it makes sense to give to this list only one parameter, only the type. Yeah? So this is a list of integer. Well, I could, if I wanted this example to be understood as a list, I would just write list of 1 underscore, and the system would give as an answer to me, it's a list of string. These lists of strings and lists of integers are the things you may know from ML, from Haskell. What is new is this notion of size here. Yes?
But a list does not have a fixed length. A list does not have a fixed length.
Well, neither a list nor a vector has a fixed length. But you can ask
in one case that, am I right in saying that in one case the length is part of the type?
That's it.
In the other case, the length is not part of the type.
Exactly. Yes. There is. Obviously, I can ask. Given a list, I can ask, how long are you? Yeah. There's a function available. Tell me the length. Yeah, this. Just looking at these without all this. This is understood as a list. This is something of length 4. Understood as a vector, it is also of length 4. This is something of length 2 because there's 2 elements in there. Yeah, there's the difference is that in the vector case, this is part of the type. Yeah, this you may have not seen before. Yes.
Sorry to derail so early on in your introductory slide. I'm curious what would happen if, for example, in the final line, rather than having hello world, you had a nested list or a nested vector. Would the type be derived as a vector or as a list?
It would be a nested, a vector of another list or another vector.
But how would it, so from the first 2 lines, it seems the response you get is depending on the partial type you give. So in the first one, you give a partial type of a list and it derives of integers. You give a partial type of a vector with 2 undefined, it gives you a 4 of integers. In your final one, if rather than hello world, you had hello had been replaced by the list or vector 21759, the second one was 21759, would that give you, it's a vector of 2 of vectors of 4 or of lists of integers?
I'm not sure.
How recursive is it?
I think we should go on and we'll become clear.
Okay, so
I think you should go forward.
okay, one remark. I'm not sure if I understood your question completely, but let me point out this is strict in a sense that all the elements, let it be a vector or a list, have to be of the same type. Yeah. So this is a string. If the first element is a string, the second has to be as well. If the first is an integer, the second and so on have to be integers as well. There is other data types. There's heterogeneous lists. Yeah, that may be the answer to your question.
We can discuss it later.
Yeah. Okay.
The question was really whether the type definition could be nested. So could you
Yes.
have square brackets inside the square brackets?
Yes, yes, there's all kinds of
And
possibilities.
what would come out, a list or a vector? Because it looks to me like a list and a
Okay.
vector are the
Well,
same.
okay. If there's an ambiguity, the system might answer.
Unknown.
Well, please be more precise. Please use the function. Tell me more precisely what do you mean, yeah, by this notation. If it's ambiguity, it's because of the bracket notation. The system will give the
Sure.
appropriate answer. Yeah.
Okay.
And you can presumably nest the round bracket bit
Yes.
and tell it whether it's vector or vector list or
yes. I
by
can.
nesting those round brackets.
I can so this first entry is always a natural number. This is
But the second one could
but
be
the
a
second is very general, can be anything, yeah. So it could as well be another vector of something, yeah. So this can be nested.
So the final argument could, for example, be vector, or it could be vect underscore open parens vec underscore underscore, and then it would derive this is a vector of length 4 of vectors of length 4.
I think so. There's no limits in
Yeah, of course, yes.
in
Yes.
getting complicated
Yes,
types.
there'd be an
yes.
ambiguity if you didn't
Okay.
specify it, but you can specify it.
We
Yeah.
normally call a vect array in most languages, wouldn't we?
Yeah. Okay.
Or
The array is a data structure that is very commonly used in these imperative languages, and they have a notion of a state that you change. Yeah, I don't. Do you have arrays in Haskell and ML?
No.
No. You have lists. Yeah.
Yeah.
So this is from. I haven't mentioned this, but these dependently typed languages are, in a sense, function languages.
Mm.
Yeah? So this is just function languages with. So all the things you have learned from Haskell or ML will apply here as well. It's just function language with a more elaborate type system, like as elaborate as it can get. Yes.
Now, when I was a very young man, I used a language called APL. Have you ever heard of it?
Yes, I've heard of it, but I've never used it.
Okay.
I'm not.
It was designed by a guy called Ken Iverson, and it had basically no type definitions whatsoever.
Yeah.
And it was designed for engineers really, and the advantage of that was supposed to be that they didn't need to worry about that, and the type was always inferred.
Yeah.
So I'm wondering whether your motivation is that same motivation or whether it's something else.
Well, my motivation. Let me go on, because we have a lot of slides. I'm glad that you participate.
Please go on.
Okay. So this is. I felt the need to say a little bit where those dependent types are coming from. Yes, this is just, and I have just 2 slides. Then I will go on and talk about examples and so I don't want to make this scary. I have not bothered to look up in books or on the internet when this expression dependent types was first used, but this is more a list of slogans to keep in mind, yeah, very rough ideas. So the lambda calculus may be familiar with you as a model for what I called the mechanics of computation. Yes. And what's surprising is that those theories were invented much earlier than computers in the 1930s. Yeah, but you may know this already. Type systems were introduced to distinguish certain classes of valid programs and predict their behavior. So they were. That's not saying a lot. Yeah, that's all I'm saying about type systems. Yeah, and sometime during these early days, someone thought about the idea of dependent types. I'm not going in any more detail. What will come up again and again is the discovery of the Curry and Howard, two different people. It's called the Curry-Howard isomorphism, and this is like the shortest, this is like a slogan way of expressing it. Yeah? If I write down something x colon t, you may used to reading this, well, x is of type t. This is whatever it may in Haskell will be double colon, but that's the idea. Yeah? X is of type t. You can read this as well as x is a proof of t. This may not be familiar with you. So it's the same, it's one thing, and it can be read in different manners. Yeah? And this is the so-called, so it's making a connection between something that comes from logic, a proof are things from logic, yes, and other ideas from programming. Yeah. So basically, we are saying if this x, normally you say a certain expression, a certain program has a type. Yeah. So this x, this program, which has a type, can also be understood as a proof of this type. Yeah? So get used to this idea. This is.
But we normally think of variables as having types, and what you introduced on the previous slide were variables with types.
Yeah.
And you're generalizing that to the idea of whole programs?
Well, it's yes, I do. Yes, so you can.
And aren't all programs functions? Isn't that it?
Yeah, in a sense. Yeah. So I mean, these types in the most simple cases, think of a type of something like a string, an integer, a little more advanced, a list of something, a vector of something, but then a function has a type as well, yes? Mm-hmm. And so if several functions work together, that's the type of the program, yes? So you're building from little pieces, bigger ones, yes? Can be even. So if I say a program has a type, this is very general here. This can be a small piece of a program, or it can be the complete program. Yes. Okay. This idea, this Curry-Howard isomorphism, comes at the cost of constructive logic and terminating programs. Constructive logic is similar but different to classical logic. It has all the derivation rules of classical logic except one, and the thing is, it requires you to have proofs, to have witnesses as proofs. What is not allowed is this what's called the law of the excluded middle, this contradiction, yes, because I don't know. Assuming that this will hold would lead to a contradiction, so it cannot hold. This is a reasoning that is not allowed. So it forces you to have witnesses. Yeah? And I want to be a little faster. Yeah, sorry, but I'm happy for your question.
By witnesses, do you mean cases, examples?
By witnesses, I mean pieces of programs. Yeah?
Instances.
Yeah, this is
you're saying,
expressions. Let me briefly, and I will try to be a little faster. Let me briefly talk about the last point. The other thing is total functions. Yeah? Functions have to be defined for all cases and have to terminate. All I want to say is these general ideas come up in the day-to-day work in working with iters, for example. Yes. So to hopefully give an answer to your question, if I later on, if I talk about some function, if I read out what does this function do, I may well read this out. Given a proof of something, this function concludes something. Yeah? So that you may not be used to reading a function as given a proof of something, but this is day-to-day work. And terminating programs, these total functions come out again and again as well. So let me be a little faster. This is, so the Curry-Howard isomorphism in the simplest slogan style is reading this x colon t in these two manners, but there's more correspondences. It actually is always a correspondence between notions of logic and notions of programming. Yeah, so they will get more familiar as we work with them. We will see, I won't go in details here, we will see something of a dependent product, a dependent pair later, and this can be understood as an existential quantifier, I guess. Existential quantifier is something from logic, so it's the connection between logic and programming. This is not too scary one, this is rather, and I got this slide from Simon, my supervisor. He had given a talk on type theory, so there's more in this slide than I will mention in my talk here. Okay, so I will go through, so we have seen vectors, very simple vectors. I will go through vectors, natural numbers, bounded natural numbers, and they're all inductively defined in a couple of slides, yes? And by the way, we will learn how to interact with the system. So one thing is we can ask the doc command tells the iterative system, well, give me some documentation. Yes, and I have on a slide not too far away, I have a summary of the things that should help you get started. Yes, so doc is just one way of interacting with the system. Well, give me some documentation. I can more precisely ask the type of a function, and I can do more. Yes, I skip that. So if I ask the system about this vector type, well, it's very similar to lists, really. Yes, and it's on the next slide that we will see both. Well, the list can be empty. Yeah, so can vectors. So there's the nil constructor, and there's a cons, a means of taking an element and a vector and yielding another vector. Yes. So what's the new thing here? Well, look at these details. Yeah. Well, we have an x element. We have the vector x of x's, yes, and the result type is very similar, but look at this. This vector had length k, and the result vector had length successor of k. Is one more. Yeah? If I attach one element to a given vector, well, the result vector will have one more, and that's expressed in the type here. Yeah? It is so these vector so that's, well, should I skip there? So these vector types are in a sense not the simplest example possible because they make use of another type. They make use of the natural numbers, yeah, but they are fairly standard, yeah, and they're useful, yeah. So so if we have asked the system, well, tell me more about vectors, this gives you a clue what's going on here. There's some explanations, but it does not help you to write your own functions, yes? And so what I've done here is written my own vector function, yeah, and written my own list function just to contrast this list function should be in the style that you may be familiar with. And in the list case, this is what you may be used to, yeah? If I have an element and I attach it to a given list, well, and it's a list of type elements, then the result will be also a list of this element type. Yeah? Element is the type here. You may be used to seeing this as A or alpha, a type variable. It's just more wordy here, but also more precise here too. So yeah. Was there a question? No?
As you asked,
Yeah.
Your null constructor, it looks, I expected it to be the empty list, but it appears not to be the empty list or the empty vector. It appears to be of type of an integer with an element. Surely.
So there's two nil constructors. There's one for list, I call it L list
Yeah.
for list nil, yeah, and V nil for vector nil, yeah. This is just a list of some type.
I confused myself, I understand.
And in the vector case, well, the nil has length 0.
Yeah, it's the type, not the instantiation. Got it.
Yeah. There's, I should not.
It's fine, Mike. It was a bad question by me.
Okay. I just continue. So how did I get this information? The idea, how would I write this vector and this functions myself? Well, it's obviously a good thing to look at the existing rendered documentation. This is very similar to what I can ask on the prompt. Yeah, it's just rendered on a web page. Yeah? It's like the source code. It's in the source code there are documentation comments and they are taken out to have a nice clickable web page where you can read the documentation and click from one function to another. And of course, it's also a good idea to look at the source code itself. Yeah, if you were more adventurous. So that's where I cheated, yeah? Okay. This is nothing new or very few things new. We have seen very simple vector examples already on the first slides. Yeah, this is just to remind you that this notation, if I write these brackets, is just a shortcut for writing what's really underneath here. It's an element 7 attached to the nil element, and so this is a vector, and this is the cons operation on this vector. So it's built from little pieces. Bigger pieces are built from little pieces. And I can use this self-defined. This is, remember I had defined these vectors myself, where I call these operations vcons for vector cons, where I can use them in a similar style. These correspond to each other. Yeah, if I 5 vcons 7, those are really the same. I just don't have the comfort of these bracket notation, yeah, because that's a syntactic thing that's meant to make life easier. I don't have them at hand for my self-built data structures. Okay, so natural numbers. I mean, the vector made use of these natural numbers. We have seen this here already, yeah? So the size of the vector is a natural number. So we need to talk about natural numbers. In the way they are simpler, there's less going on here, yeah? And, well, this is just a piano style of defining natural numbers. A natural number can either be 0 or successor of another natural number. So there's a very nice expression. Aaron Stump has written a book about Agda recently, and he calls this kind of definition caveman's definition. Yeah, you remember our ancestors in the caves, if they would count something, they would just make another mark, yes, and in the end, if they had counted whatever, you would count the marks. This is what's going That's an interesting thing. That's very similar to natural numbers, but it's finite natural numbers. And again, I have 2 slides for this, and again I tried to start with the easy part of using it. Yeah? If you don't know, if you don't have an idea what's it all about, well, play with it, yeah? So, really, a finite number of n is a natural number that is bound by this n, that is less than this n. And I hope you agree with me. And here's 2 examples of its usage, yeah? If I, what is in this set of fin of 5? Well, there's the 0, the 1, the 2, the 3, the 4. Those are the possibilities. They are all smaller than 5. Yeah? 3 certainly is in this set. Yeah? The system answers with this. So with this complicated thing. So this 3 can be understood in different manners. Yeah, we have seen the number 3 understood as an integer. It can also be understood as a natural number, or it can be understood as a finite natural numbers. And well, again, if I want this 3 to be understood as a finite natural number, as I ask the system to do with this the function, then it answers with yes, it is of this type, finite 5, yeah, that is less than 5, and is really 0 plus 1 plus 2 plus 3, yeah. No, so it's 3, yeah, so 0 plus 1 plus 1 plus 1, yeah, that is 3, yeah, sorry. And you can read this, I mean, you are already maybe used to reading this Z as 0 and the S as successor, and you may just read this as finite 0 or finite successor. Yes. Then
what is the type of finite 0?
What is the type of
FZ?
FZ?
It's defined at the top.
It's a literal.
Well,
What is its type?
This is a type.
FZ?
Yeah, I mean, any FZ, a fin of
Oh, it's the
0.
empty bounded type.
Well, you're asking what is the type of fin of 0? Yeah, is
No, I'm
that
asking what is the type of F of Z, FZ? Is that a type or a value?
FZ itself is a type.
It's a type, and what
Yeah.
is it? What type is it?
And so you're asking
It's the
what
type
is the
of the
type
range 0
of
to
something
0.
that is a type? Is that your question? Yeah.
Sorry?
And
What are its values? What is it? How do you define it as a type?
FZ is a constructor in the type fin5. And it's just saying this is the constructor set of calls that you can go through to get to that value for 3.
Well, that's what I'm asking. Is it a constructor in fin5? What is the type of FZ?
If you go back to the one where you showed the list, you go the list examples, it'll become clear. Just go back a few slides. There you go. So you have v0. It's the same as v0. And if you go back one more, you'll see
No,
that
it's not the same as v0.
it is. Go back one more.
It isn't the same as v0. What is FZ?
FZ is a type.
And what type is it?
It
How do you
is,
define it?
well, if I would write this down, I don't have a board here. It would be all the natural numbers that are smaller than 0. Are there any? I'm asking.
Okay, fair enough. That you define it for me. Thank you.
Yeah.
That's fine. It's the type of the range 0 to 0.
Yeah.
0
There
to
are
1.
none.
There are none. It's an empty type.
It's an empty. It has no inhabitants.
Well,
It's
you've answered my
inhabitants.
question.
Yeah.
Thank you.
So that's an interesting thing. And I was just about to come to this. So here we have seen how to use them. Well, here's the definition, yeah? Again, I'm asking, tell me more about these finite natural numbers. And yes, this is an interesting thing. Fin of Z is a valid type, but there are no inhabitants. You cannot tell me any natural number that is smaller than 0, can you? No. So it's not These are the constructors. So you can, and S of k is the successor of something. If k is a natural number, then is this the successor of some natural number? It must be at least 1. It can be 1 or 2 or 3 or 4 or 5. So in all those cases, fin of 1, fin of 2, fin of 3, there are examples. They are inhabited. Yeah?
Yeah.
Fin of 0 will not be inhabited.
Sure.
Okay? Okay.
So here's a different question. Why is it defined such that it's strictly less than rather than less than or equal to?
Because that's where you
Yeah, I
choose
mean,
to
there
store it.
is. It could be defined differently. It's not that. I found it initially. I found it a little confusing myself because I tend to think about something that is bounded, like the upper bound
Yeah,
included. Yeah. It turns out that it comes in very handy like this. And we will see a couple of examples where these fin things are used together with vectors, and this just makes sense. Yeah.
Okay.
And get used to these patterns. I mean, this is really saying a lot. This is fin is defined. Fin is possible for fin of 1, 2, 3, 4, 5, 6. Fin is not possible for 0. I mean, the type
Yeah.
is possible, but it has no inhabitants. That's the point. So that's the first time I'm mentioning this thing, patterns. Yeah, patterns of what? Of using natural numbers in vectors to say what is allowed, typical patterns, and this will come up again and again. So a little faster. That's the head function. Yeah, you know the head function from list in ML, in Haskell, yeah? Well, there's a head function for in the vector case as well, yeah? What does it do? Well, let's look at this example. Well, given a vector 5 and 7, 2 elements, well, give me the first element, the head of this thing. It's no surprise here, yeah? But look at this type. And what would happen if I call this vector if I call this head function on the empty vector? Some mistake, yeah? It's not defined, yeah? So the system answers with some error message, yes? But the interesting thing is, this is a type error. This is not an exception. In Haskell, when I come to this, hopefully, here, yeah, this is the Haskell counterpart. If I do the same thing, if I call the head function on the Haskell list with these 5, 7, there's 2 elements, 5 and 7, well, I got some error message as well. Yes, system has failed. This is an exception, yeah?
Just a point of information, people might not know that in Ada, types are defined on index types. You know, and a vector or array is defined on an index type, and that index type is a bounded range. And so it's a type question as to whether your index is out of range. So it's, in Ada, it's like this.
Okay, so Ada has
Ada's
maybe
not a
some
functional
ideas
language.
of
It's
these.
not a functional language,
Yeah.
but it has
Okay.
this sort of approach.
Yeah. So, and what you're pointing at, these bounds, safe accesses of vector, we come to in a second, and the next example. Yeah. So let me skip back. In both cases, in the case of Idris, we get some error message. In the case of Haskell or ML or whatever you're familiar with, we get another error message. But there's a fundamental difference in that this is an exception, something that occurs at runtime, whereas this is a type error. This may not make much of a difference to you as long as you're working on the command line, as long as you are in this type in something, let the system give me an answer, read our REPL, yeah?
Yeah.
Run eval print loop, yes? It's a nice way of getting in contact with the system, yeah? But imagine now that you're type checking, that you want to be sure that a more complicated piece of program works, yes? Type errors can be detected at compile time beforehand, yeah? These runtime exceptions are things that will creep up at runtime. That's a fundamental difference. Yeah.
So it would be fair to say that this is strongly targeted.
Yes.
Yeah.
I don't want to talk too much about this. I couldn't resist to include this anyway. Let me explain this like this. I'd like to say, if you get the idea of these dependent terms, you may want to try them out. You may take in Haskell or ML program that you have written and try it out in Idris. And I'd like to say that Idris should not get in your way. It should be fairly easy. You remember we had these introductory slides, we had lists in Idris as well, not only vectors. So lists is one option. You can just try to reprogram an existing little thing in Idris, making use of lists. Yeah? I'd like to say this is not getting in your way, there's no difficulties. The truth is, it's a little more complicated than that. The type of this head function in Idris is not is not exactly the same as this simple type of the head function in Haskell. Yeah? It's a little more complicated. Right? Basically, it takes a list of A and returns an element. Well, that we have seen here as well. But there's something in between. Well, why is that? Because, remember, we said functions must be total. We must take into account the possibilities that I call this head function on an empty list. And so this function only works if I have a proof that really the list at hand is not empty, and the system does everything it can to come up with this proof automatically. Yeah? So this is hopefully not disappointing you. You should be able to ignore these pieces more or less initially. You should not be surprised. That's the reason. Yeah? Because of these totality constraints. Yeah? We cannot, we must define total functions. So we must take into account the possibility that the list is empty. And if that is the case, this additional proof will reject it. I will go on. Here's an example of, we have seen these finite natural numbers and these vectors, and here's an example where they play very well together. And this may be an answer to your question, why is the upper bound not included? Well, if I have a given vector, this would be element 0, this would be element 1, this would be element 3, this would be element, 0, 1, 2, 3. Yeah? So this index or lookup function, well, it is allowed for all the possibilities. I can call this index function asking, well, give me the second element. This is the 0, 1, 2. Well, this will be this element, yeah? And it will. And it just turns out that with this fin definition, as we saw, that the upper bound is not included, well, the fin of length n goes very well together with the vector of length n. because it's just one small. Is that okay? Is it? It's getting more complicated now. I'm glad you had asked questions before. I need to go a little faster, and I hope I'm okay. So this is. So we have seen. This is a slide showing functions that should be rather familiar to you if you have used lists in functional languages. Yeah? And some of them we have seen. There's some new ones, yeah? And they are vector counterparts. And so we have seen, for example, the head function, yeah? And the head functions on vectors we have seen as well, but it is more precise. And in that, it requires us to give it a vector that has at least one element. It can be the empty vector. Yeah? This is the index function or lookup function. Well, again, the vector version is more precise, yeah? in that it tells us what is possible, in what bounds can I possibly call this index function. Yeah? And there's more examples. Yeah, this is. You don't have to go through all of them. Yeah, maybe let me take two of them. Maybe append. Yeah, you have one vector or list on the left-hand side, one on the right-hand side. You just append them together. Well, you have like a bigger list or vector. Well, in the case of the list, you don't know much more about the results type. Well, in the case of vectors, you know that given a vector of length m and a vector of length n, the result type must be the sum of those. Makes sense, yeah? Doesn't it? Yeah. And there's more. And so there's something that I've mentioned before. There's these patterns that come up again and again. Yeah? There's pattern. This is the pattern of a sum. This is the pattern of something that cannot be 0 because it's at least 1, maybe 2, maybe 3. This is not strictly Idris notation anymore. This is why I've written Idris vector function or variation thereof. Yeah? Map is defined in Idris not for vectors, it's for functors, yes, but it's good enough for our understanding to think of this map function here as something that is length preserving. Yeah? If the original vector had length n, then whatever I do to each element, I can be sure that the result vector is of length m as well. Yeah? So this is another way of reading this. It's preserving some length, for example. Yeah? This is similar, okay, a notation that it came up with, rather, that should get across the idea. Yeah? If I filter out some elements, well, the result will be have usually less elements. Maybe at most you will have the original number of elements. So this is like, it's not in Idris, but it makes sense. Yeah? And once you get the idea, feel free to use your own notation, yeah, to just scribble down ideas. So I talked about these patterns, yeah. So we have seen the successor of something. Well, can come up in two ways. Yeah, can be a function may take something of length m and yield something of length m plus 1. Yeah, that's the successor. That is the function. It's the cons function, for example. Yeah, or it can be used in a manner like something that cannot be 0. Yeah? Because it's at least 1. Yeah, and we have seen the other patterns as well. Okay, here's something in which way these dependent types could be useful. Yeah, you may know from school or from the algebra what's it to multiply some matrices, yes, and you have, I haven't bothered to fill in any numbers here, but think of this as an n times m matrix and this of an m times p matrix. Well, the result matrix will have this shape, and you may have your own way of remembering this. It always helped me to just arrange these matrices in a different order, like the first part here, the second here, and then you kind of can see the dimensions of the result matrix, because any element here will be like, this element here will be like this times this plus this times this. Yeah, that's this. Yeah, this is, you know this, yeah, from school or from wherever. And so it's not by accident that if this has 2 rows here, this must have, no, if this has 2 columns here, this must have 2 rows. Yes. And what can be dependent types worth in this case? Well, we can denote this. Yeah. So this vector can serve these vectors if I nest them. Yeah, I think this was a question some time ago. Can I nest those things? Yes, I can. Very well. This is a vector of n lines, if you so want, and each line has m columns. Is this right? Yeah, I think so. Yes. And here a vector of m lines of p columns, and well, the result type is written as a one. So it's more precise. That's the whole point of what we're doing. We're using types that are more precise. Yeah? You agree with me that it's more precise to talk about natural numbers that are at most 5. It's more precise than just talking about natural numbers. Yeah? This could be anything could be useful. You think of a calendar application where days are between 1 and 31, and months are between 1 and 12, and things like this. Yeah? That's the whole point. Yeah? Dependent types are more precise.
Compile time or runtime?
Pardon me? At compile time, yeah. That's the idea of types in general. Types is to detect errors at compile time. Yeah? Okay, another thing, and I have to watch my clock. I will be fast enough. Another idea.
So,
yeah.
What these types are doing is making it simpler to construct proof.
Well, yes, well, if you say like this, making it simpler to construct proofs, then I may ask you, well, why do you want proofs in the first place? Yes.
Well,
so I'd say it a little differently. To have proofs of something is a very strong idea. It's stronger than testing. Yeah? If you may be very used to test suits, unit tests, and there's all kinds of tests. Yeah, you test 1,000 cases. You hope that you have covered the typical cases. It's still possible that there may be some edge cases.
It's
Getting in that you have not thought about, yes?
It's not just possible, it's likely.
Yeah. So, proofs are stronger,
Yeah.
And we must, if we use those types, the system requires us to come up with those proofs. And this is not always easy. It's getting more complicated, yeah? Because it's a different discipline, yeah? It's not, so programming and proving are the same thing in this environment. Yeah? You may not be used to thinking of programming as coming up with proofs. Yeah? And there's this has its own difficulties, if you so want. Yeah? You may be a good programmer that knows how to break down very complicated problems into small, digestible pieces, yes, and you may not know how to get something through the type checker, something that is a very common thing. You have a relatively rough idea that something should hold true, and this is just an idea where this is possible as well. Yeah? Sorting lists. We can specify what does it mean to sort a list. Yeah? Well, a list is sorted if the sorted list has exactly the same number of elements as the original list. Yeah? So the number of elements. If more than that, if it's really a permutation of the original elements, it's not only the number, it's really the same elements you find. Yeah?
Yeah.
And if in the sorted list, if you pick any two successive elements, they need to be in order. Yeah? So that's the specification. Yeah? I'm not saying that it's completely easy to yeah.
How far through the 2/3 are we at the moment?
Well, not enough.
Give me an estimate.
Yeah. I have a number.
No,
now,
you
so
owe
I
it to
don't
your
know
audience.
whether-
Give me an
okay.
estimate. How far are we through the 2/3?
The audience was caused it to run slowly.
Well, that's why I'm
Yeah,
trying to
okay, okay.
propose a method of proceeding.
I cannot give exact number, but I know I have to hurry a little on. Yes.
No, you must give me an estimate right now.
From the first, we have covered more
Are we
than
halfway
half.
through
We
the
have
two-thirds?
covered more than half of the first part.
Okay.
And I'm happy if I get across some ideas, and if we don't touch the more ambitious ideas. I'd be more happy if you have questions. I'd be happy to leave out some. All these proving things can get terribly complicated, yes, and so we don't have a chance to understand it completely. I'd be happy to leave out, to skip something, yes.
Well, I do think we should proceed a bit faster,
Yeah,
and I think
yeah.
the speaker should discipline himself to move faster,
Okay.
and the audience to be more restrained with their questions.
Okay, thanks.
I hope
thanks.
we could agree
Yeah.
to that.
Thanks for reminding me. Okay. So this is something where these dependent types can come in handy. I'm not saying it's easy to come up with proofs. Yes, it's a new discipline. Yeah. Okay. Briefly mention this. Another type is dependent pairs. I'd like to mention this because it was announced in the abstract of my talk. Yeah? Typical examples of dependent types are vectors and dependent types. You should have seen this at least. But if I have a read function that reads some element, I don't know, in a vector, I don't know beforehand how many elements I will read. So really, I get a vector of some length, and really this can be understood as a pair of some length n together with this vector of length that depends on this. Yeah. And this is in the very beginning I pointed to existential quantification. You can read this as well. There exists a length such that reading those elements yields a vector of this length. Oops. This is general, very general. This is not very detailed. We have seen vectors. They are stronger than lists. They carry the notion of a size, and there's many more other examples, and it's a good idea to make use of them. One example is these stronger types, stronger than Boolean types. Yeah, you know Boolean types, yes and no. Yeah, and you in the course of in working with these dependent types, you will come across these types that read yes because, no because. So they have the notion of a proof. They carry around a proof.
Sorry, I have a quick question on the previous slide. With that previous slide, so that now cannot be checked to compile time though, is that right? Because this is dependent on data we're reading from somewhere. And until we've got it, we don't know.
Anything can be checked. And any types are checked at compile time. But because we don't know what, we cannot just say the result of reading this vector is a vector of length n. We must say, well, there is some n such that the result will be of this length n. Okay, let me say at this point, these dependent pairs are maybe, they're relatively simple here, but they're slightly more ambitious to understand why you need them. If you don't see, if it's not obvious for you, that's fine. Yeah?
Isn't the point here that having read the list, you know how long it is, and that length is now available for succeeding checks?
Yeah.
Yeah. Because otherwise, normally a program that reads a list will not tell you how long it is.
Yes.
Unless you out program it to do that.
Yeah.
And that's a runtime.
That's a
right.
Yeah.
Let's just move on. Yeah, because I mean, I could possibly only explain this to you if I showed you usage and.
I think it's quite straightforward actually, because if I then do something that says copy this vector to another vector of size x, and x is not equal to len, then it will tell me there's a problem.
But that's a runtime.
Yeah.
That's a runtime too, you're right.
It's not a functional thing to do.
So let me just.
Well, that's true.
We have seen in the vector case, this type of the vector depends on a value, right? Like the vector of size 4 depends on the value 4. And here is this type of this pair depends on this first part of the pair. The whole thing is a type, and the second part of this type depends on the first. So that's dependence. Yeah? Maybe that's the way to read it. If it's not immediately useful to you, how you want to passively use it, why you need to use it, read it as some dependency. This length comes up here again. There's a dependency. That's it. Okay. I'm not going any detail here. I will just say proving can be a difficult thing. This is something from the master thesis of Dr. Christiansen, who is very engaged in the IDRIS community. Is just brief idea. If we this function here is much more difficult to prove than the function here. The only difference is really.
What do you mean to prove a function? What do you mean by to prove a function?
To come up with a program that has this type.
As what? This type?
This is the type. This is
Okay, to show a program of this type.
Yeah.
Okay.
To find a program, the type I'm giving to you. Now come up with a program that has this type.
Yeah, sure.
Yeah? Find something. Find an inhabitant. I cannot go into detail. I'm just pointing out this is very similar to the above. The only difference is this plus function, which is slightly unusually defined here. And in this slightly unusual definition of the plus function made our proof efforts much harder. It's okay, hopefully, yeah? Yeah.
So this is sort of like program synthesis from a type spec. Is that
No. That's okay. Let me. Okay, this is okay. I come to your question in a second. And I can answer your question. I have 3 or 4 slides that are like my transition to the next part. So we are at the end of my first slide. There's 3 or 4 slides that can fall in both categories. Well, you are asking how do I work with this in practice? You may be used to Haskell, the type inference in Haskell. You just write down something, and the system infers a type. Yeah. In practically speaking, In iterates, you usually work the other way around. You write the type, you have an idea what your function should do, and because this type is very precise, it's more precise than in the list case, it can construct for you a lot of simple, it can break down your functions, it can provide for you a lot of code, skeletons of a code. You just have to fill in some missing pieces. Yeah? There's very good talks by Evan Brady and David Christiansen who show how to use it. This is very connected with the editor, but it's too complicated. And I could show it only on this computer. Yeah. So, is this hopefully getting? Yeah.
Yeah.
This is how you do it. Really. Where do you start? It's a good idea to start with the type, and in iterates you're forced to start with the type more so than in Haskell. Yeah. Okay. I've learned, so in the second part of my talk, I want to talk about what I'm doing in a similar but smaller language, Py4. I learned a lot about how these things work from working with this Py4. There's some key ideas that I'd like to get across. If you look at, and I learned them from Py4, but they apply to iterates as well. So if you look under the hood, if you ask yourself, what does a dependently typed language look really? How is it implemented? If you start out wanting to write a compiler for this, that's an ambitious effort, yes, I admit. I come back to this slide in a second. You typically have in a functional language a data structure for expressions and another data structure for types. Yeah? Here's an example. Here's a couple of examples. Yeah? If you have 7 is of type natural number, or hello is of type string, well, this would be encoded as an expression. This is just the simplest possible expression: variable, abstraction, lambda application, and there's more. Yeah, but you usually start with a simple model of the lambda calculus and you enrich that. And this is the type. This will be on the other side. Yeah, so everything that is in this blue, it's a little gray blue, is encoded in this type, in this data type. This is the data type. This is the Haskell data type for types. Yeah, and this is the Haskell data type for expressions. And there is a connection between them in a sense that the type reflects the structure. Here's a slightly more complicated thing. Yeah? So this is a pair of a number and a list of things. Well, what I see on this left side is reflected in the type. It does not come as a surprise. Yeah? But really there is a clear cut between those. And they're not, and now I'm going back, as in dependently typed languages, they're not one and the same thing. In independently typed languages, you use one thing, because at any point, yeah, if you remember this vector was depending on a value, so these types depend on values, so they're all kind of intermingled, yeah? So one idea is just to have one data structure. It would not necessarily have to be this way. You could have 2 data structures and they would be mutually recursive. Yeah? But that's a good way of thinking of this. It's like this in iterates, it's like this in Py4. And there's 2 more things, and then I'll talk 2 more things that I'd like to get across as central ideas of these dependently typed languages. Well, again, I hope I'm not making it too difficult. You may know this lambda expressions. Yeah, this is a function. Given a parameter, an argument x, well, this lambda does something to the x in the expression of the body. The body depends on this x. Yeah? And I've chosen this because this is a typical example of a binder. The lambda abstraction is a binder. Yeah? And in the way you have seen function types is like this. Well, a function that takes some A to some B. And what is new in functional languages is, well, this is a function as well that takes an A to B, but this B may depend on some value in X. That's new, yeah? And so really this function type constructor, this error, is a binder, because this X can occur and the type on the right side, just like this. Yeah? So the function type constructor is a binder. Only in simple cases we can write it as short as this. Very briefly, I learned a lot about these dependency type languages from a couple of talks by Stephanie Weyrich, who has also created this Pi4All language that I'm going to talk next. That is all video recorded, and the main idea of her talks is, I mean, it's interesting to think about how does this type checking work internally. Yeah, it's not an easy to explain thing, and one broad, very rough ideas is that in each case you have typing rules in two flavors. Yeah, you have a rule for checking, but someone's given a claim. I claim that this has a certain type. Just check it for me. Yeah, or I give an expression. Tell me the type. Infer the type. Yeah, so they have different preconditions. Yeah, I mean, just checking something is in a sense simpler than inferring the type. Yes. Okay. So now I come to my research. I have a little bit of time. Yes. So I started out with the idea of doing refactorings for Idris, and it was a little overwhelming very soon, because it's a language where a lot of people are working on this. I was new to these dependent types as well, and I very soon decided to tackle a smaller, more manageable language, and this is this Pi4All language, which definitely right. It's less capable. You would not want to do a lot with Pi4All yourself. You'd rather want to work with Idris, but for understanding things, this came in very handy. Yes, and this is an outline of the things that one encounters when the aim is to do some refactoring on these languages. I talk about parsing. I have chosen some libraries. I have just chosen them. They're similar to the original Pi4All libraries. I learned a lot about this. And we need to do this parsing in a manner that is a little unusual, because normally you know the idea of an abstract syntax tree. Yes, you forget about all the unimportant part, the white space, but in refactoring, the idea is to take a given program, do some kind of manipulation, and come up with a better program, and you want to preserve the comments. So you have, parsing is more demanding, yeah, because we want white space aware parsing. And there's a couple of slides that I will skip, yes, but they are in there, yes. So once we have parsed the thing, well, we need to do some manipulation in this tree. Yeah? We want to replace some part of this tree with maybe another part. And a very helpful data structure was the zippers. The zippers allow us to go up and down, the left part and the right part of the tree, yes. So this is the data structures that are the result of parsing are encapsulated in this zipper, and the zipper does allow me to walk in any direction in the tree that I want, and to replace part of it. And now, well, these are my current efforts. There's, as these dependency type languages can, in a way, be seen just as another kind of functional languages, all the things we know from functional languages apply to them as well, and there's a wealth of knowledge about how to refactor even functional languages that is knowledge in our group. Yeah? And I'm being more ambitious here in making use of these dependent types. Yeah? These lists to vector refactorings. That's what I'm working currently on. I will mention this very last topic only now, not later. These lists to vector refactorings, I'll come to them in more detail later. They can be seen as just a data type refactoring. Another data type refactoring is list to tree. And list to tree would work even with a language like ML or Haskell. This last point is more general. It applies to all kinds of functional languages. This is the most ambitious effort. Okay. There's a couple of slides about what is refactoring. You know, you have heard the term refactoring before, yes? Is there anyone who has never seen a refactoring? It's let me come up with this slide. I like these rough analogies. If a compiler is something that translates one language to another, think of translating English to French, then a refactoring tool is something that does improve, that changes the structure within a given language, like the editor of a journal. Yeah? A friend of mine was in journalist school, and he told me his teachers took his text, took it apart, assembled it, cut out most of the pieces, assembled it in a hopefully better manner. That's what refactoring is about. Yes? There's some experience in our group with other refactoring tools, Hare for Haskell, Erlang, Grammar for Erlang. This is where I come in. Parsing. I have several slides of parsing, and I will mostly skip them. I will mostly skip them because all I want to say. Let me say just a few remarks. If the programmer has written down a if then else statement with lots of, to him or her, precious comments, yeah? We don't want to lose them. That's all I'm asking for. If normally the outcome of parsing this is an if statement like this, well, if I want to preserve those comments, I have to come up with a data structure that takes all these possible comments in between into account. Yes? And it does work. So for every data structure, the if is the data structure that represents the if then else statement. Yeah, there is a corresponding data structure in my code with an underscore that is what I call the white space aware version of this. And this is how it looks in the code. This is an example of how it's used. I'm skipping very fast through this. If at all you are interested in the details, I think there's something cut off. I have to, in the slide that I will put on the internet, I think there's one line missing here, an interesting line missing here. Somehow you have the white space that you normally throw away. That's the usual thing that you do with white space, you have to keep. Yeah? And there's a way of doing it. Because I'm not saying it's the only way, one can do it differently. That's what I'm doing. Yeah? This is kind of a summary of what I'm doing in this parsing efforts. Let me just say why this is an interesting question. This small language, Pi for R, is relatively manageable. Yes, if I made mistakes and I have made mistakes, could take me a couple of days to get it sorted out. Idris, for example, is much bigger. If I just have the Idris parser, want to do something with it, it's much larger undertaking. And so the question is, given the existing Idris parser, could this be turned into something that is white space aware? Because we want to keep this white space. And I'm claiming no, it's not that easy. We have to do it step by step. That's all I'm saying. Yeah. Let's parse it. Yeah, what was the question?
I mean, normally when you go from concrete syntax to abstract syntax, as you said, you throw away information.
Yeah.
So getting that information back again is non-trivial.
But I don't really get it back in again. Yes, I parse it in a different way.
Okay.
In a what I call white space aware manner.
Is that considered being able to go back to concrete syntax? Is that
Yeah,
considered a critically important question?
Yeah, there is all kinds of. I gave a talk about this a couple of months ago, and it was this talk was mostly about this parsing, and there were a couple of slides. I've removed them. They show there's all kinds of transitions going. Given a concrete syntax tree, where we can forget about these white space and come up with and turn that into an abstract syntax tree.
Sure.
And this in turn can be transformed in the original Pi for all abstract syntax tree that Stephanie Weyrich had provided. And this is useful as well because I'm using the type checking of the original Pi for all. So there's all kinds of transitions between those different syntax representations. Yes. Okay. Short remark about desugaring. When usually, very often, when you look at a parser, the parser encounters something like this, lambda x, y body, or something like this, and internally encodes it as a function, a function that takes one argument and yields a function that takes another argument. For our needs, we need to be more, those are different things. Yeah? So I'm claiming it's not a good idea to do this desugaring, as it's called, on the way, sloppy. It's a better idea to be explicit about it. It's better to parse this differently than the above. And then it's clear what was written in the original program, so I can give back that. If I do desugaring during parsing, I have no idea what was the original program. Was it on this side or on that side? Yeah? The binding structure. I will skip this. There's a couple of interesting ideas. This is a very nice library that I'm using. It's the bound library from Edward Kmet, someone very active in the Haskell community. It's a little different than the unbound library that is found in the original Pi for all. I was curious, what's it about? I wanted to invest my time in something that I found interesting. If it was a good idea, I don't know, because but I learned a lot about this. Yeah, so there are some main ideas. These slides are maybe some not so bad ideas of getting a broad idea of how this bound library works, but I will not go in much detail. Let me briefly say why is this binding structure something that you want to care about. Yes? If I don't have something like this bound library or unbound library, yes, things like substitution can be very difficult. Yeah, and alpha equivalence. Alpha equivalence is the question if two terms are the same, regardless of the way of actually writing it down. Yeah. Lambda x, a function lambda x that does something with the x is the same as a function lambda y that does the same to the y. It's not a matter of using the x or the y. It's really what does the body look like. Yeah? So this is alpha equivalence. And so there's a couple of questions, and the normal way of tackling these problems is to use De Bruijn indices, to use numbers, and this can get horribly complicated. So, and this is where essentially these binding libraries do similar